Okay. So majority of the people seems like you'll use Windows 10. So first, we need to install Ubuntu within Windows 10. It's very, very straightforward, very simple. It comes built in to Windows 10 now. So let me share my screen and tell you how to do it. All right, just go to Windows Store or Microsoft Store. And type in Ubuntu, U-B-U-N-T-U. All right. When you do this, you will get many options. There's a Ubuntu 20, 18, and Ubuntu. You pick Ubuntu 18, okay? Ubuntu 18.04. You pick it, and if you don't have it already installed, you'll have, instead of launch, you will have install. So go ahead and click that and tell me if things go wrong. Okay, tell me what happened when you click it.
It's downloading for me.
Okay. Anybody get any errors? Okay, no errors. All right, perfect. So while that downloads in the background, we will install another software that we will use for visualization. This is called ParaView, P-A-R-A. Just type in ParaView download. Okay, and click the download ParaView link. So this page should give you options for, here's Windows, Linux, or Mac, all right? Pick whichever operating system you're working with and download the version that says, so there's two different options. There's one that has an MPI in it. Do not pick that one, pick the other one, either exe or zip, okay? When you click that, it'll download the ParaView installer. I already have it, so I'll cancel it. Okay, same thing for Linux and Mac. For Linux, let's see which one. Brandon, do you have a question? Okay, so for Linux, give me 1 second. Okay, perfect. So Linux, the MPI version is fine. It comes with bundled MPI. So just pick the one on top here, that one. Okay, and let me check for Mac. Let's see, unsigned MPI. Okay. So the bottom one should work fine. Oh, either the first one or the third one should work fine. Okay, let me know if any of you have any trouble.
Could you repeat the one for Windows, please?
Sure. For Windows, you pick either number 1 or number 2. Do not pick the one with MPI.
Okay, thank you.
Okay, anybody any trouble? So that will also download in the background. All right, perfect. So while those two download, they'll take some time. So I'll continue with the lecture. We'll go for like half an hour, then we'll come back. All right. Okay, so leave those two to download, and then let's continue here. All right, so if you remember last time we were talking about free surface effects. So on your boat, if you have a container that's partially filled, it can cause problems because when the hull tilts, the liquid inside will start sort of sloshing, and that changes our the G location, the center of gravity location. And we computed what this change, the shift in the center of gravity location would be. That's the G0, G1, G0 here. All right, and we can compute it exactly based on the tank properties and the liquid inside the tank. Once we know what the shift in center of gravity is, we can think about, all right, so this center of gravity has moved from G0 to G1, meaning our restoring torque has decreased because the moment arm has decreased. And again, we can compute exactly what that loss is. Okay, so that's what we'll do next. Let me see. All right. So the note we had was if the cargo doesn't move, if there's no liquid sloshing, G0 remains in its place. So that's the original restoring torque. So this is the original. And when we have a free surface effect, so with a free surface effect, this is the new arm is G1A. The force is the same, delta 0. Okay. So the reduction in torque is, so torque reduced by G0, G1 times delta 0. It's just original minus the new reduced value gives us the total difference. Okay. So that's not good because we want our restoring torque. Restoring torque is good for keeping the hull stable. Any reduction is not beneficial. Another thing we'll mark here is when we continue this line vertically, we have this intersection point. Let's call this G2. And this becomes our new effective metacentric height. Okay, G2M is the new metacentric height. Originally, it was G0M. So again, we have reduced the GM value, which means we have reduced stability. So now GM effective is G2M. All right. So the loss that we have suffered in the GM value is G0, G2. Okay, that's how much it has decreased by. So loss in GM is G0, G2. And using trigonometry, we just see this is G0, G1 over phi. All right. Again, we have a right triangle here, G0, G1 and G0, G2. G0, G1, we had an expression for this. We plug it in, and what we get is I tank rho L nabla 0 rho S. All right, so that's a very quick way of computing what your loss in GM is once you put a container with a free surface liquid in there. Is there a question?
Could you label phi on that picture?
Oh yeah, phi is the angle. This.
Yes, okay, thank you.
Yeah, so just using trigonometry, it's O over A, O over H, so sine. But for small angles, sine phi or phi is the same. Okay, so this loss in GM, now we know it depends on certain parameters. We can think about how these different parameters affect our stability. So what do you say? If we have a container with a very dense liquid versus a very light liquid, which one is worse?
Dense liquid.
Because?
It changes the center of gravity more.
Yeah, and and from the formula here on the right, can you point to one parameter?
The row on the top.
Yeah, so if you have a very dense liquid, let's say liquid mercury, but don't transport it, that's toxic. So rho L value will be very, very high. So your loss in GM will be very high. Similarly, if the tank, you make a tank that's very, very wide, it will have a very high area moment of inertia. That's also not good. So you don't want wide tanks. And intuitively, it makes sense, right? If you have a wide tank, the sloshing becomes more extreme. So both these things should be avoided. So
That's why most tanks you see are circular.
No.
Cross section.
No, so most tanks are circular because cylinder is very a wonderful shape for minimizing stress. So that's to prevent the tank from rupturing or getting damaged. If you have like sharp corners, like in a rectangle, the edges are points of failure. If you remember this, you probably studied in structural mechanics or one of your solids classes. When you have a sharp corner, that becomes a point of failure. So that's why most cylinders are circular. So if we have weird shaped tanks like a circular cross section or let's say a triangular cross section, I'll show you how we account for that in iTank. Okay, so just one before that, just writing two things. So if rho L is large, this means greater loss in GM. Lower stability. Okay. And also if I tank large, same thing, not good for stability. Okay. So for non-rectangular tanks, I tank is equal to what? So let me draw some. Let me draw a cylindrical tank. Let me draw another weird triangular shaped tank. Okay, you will never encounter this, but just to illustrate my point. So in these cases, what is I tank? How do you compute I tank?
Would you need to know the level of the, where the level of the liquid is in the tank?
Okay, perfect. So let's say the level of the liquid inside is up to this guy. How do you compute I of this?
Well, it's just the rectangle about the axis that the cylinder is on.
Exactly. So see, this is, when you look at this liquid plane, let's take a top view, it's actually a rectangle. And we know how to compute I for a rectangle, bh cubed over 12. Okay. Same thing here. If we have this funky shape, when we have the liquid inside, it will still form a rectangular plane. So we get the same thing. Okay. So just keep that in mind. Even with strange shapes, the the liquid plane ends up looking like a rectangle very frequently. All right. Then, oops. Okay, so over here we said there is a loss in GM with free surface effects. We need to be careful how to design our tanks and what liquid we're carrying. What liquid we are carrying, we cannot really decide that because we need to transport whatever is given to us. But we can decide on the tank design. So either make tanks with very small I, meaning very skinny and very tall, or if you have a wide tank, we section it up, okay? And that's a very effective way of decreasing the loss in stability. So free surface effects. Should be avoided if possible. Okay. But if it's not possible to avoid them, like you need to carry fresh water, you need to carry fuel, you need to transport oil in an oil tanker. So remedy is use tanks with smaller I tank. And this we can usually obtain by subdividing the tank. All right. And I'll show you exactly how subdividing the tank helps. So any tank with n, let's say, with n total subdivisions, the loss in GM, G0, G2 ends up being the same. I'm writing the same formula we had, I tank divided by rho S divided by nabla 0 times 1 over n squared.
I have a question.
Yeah.
So like, what if you stood the tank up and then like your planar area was like a circle? How would that affect the moment of inertia? Would that keep it the same, or would that increase it or decrease it?
Are you talking about this scenario?
Yeah. Like if you stood that up vertical, then the planar area would be a circle, right?
If we what?
If the cylinder was standing vertical.
Oh, like on edge.
Yeah.
Okay. All right. Then you get a circle. Oh, okay. I see what you're saying. So instead of laying the cylinder horizontally, you lay it on vertically
Yeah.
for carrying the liquid. Yeah, that's a very good way of doing this, because then the cross section would basically be a circle. And that has a very low I compared to these rectangles. So you could technically have long vertical tanks within the ship. Then it becomes more of a problem of, think about what you're doing. If you have this vertical tank in the ship and you place it somewhere, what does it do? Think about the weight distribution.
Raises your center of gravity.
Yeah, it raises your center of gravity up. Also, you're concentrating all this heavy liquid in one position instead of distributing it throughout the hull, okay? So there's always pros and cons. So that's the biggest con, that you're basically putting a very heavy weight in one location instead of letting it slide all over the hull, okay?
Okay.
Yeah, but what you proposed is an effective solution. There's something easier that we can do. So that's basically using these subdivisions. So let me draw a sketch. Well, first, this is the loss in effective GM. This is our original loss in GM. If we make 2 subdivisions, we decrease it by 4 times. If we make 3 subdivisions, we decrease it by 9 times. Okay, so you see, very, very quickly we can make our hull stable. So let's say if our original tank looked like this. So that's the tank, and we have liquid inside. In this case, I tank is what? It's LB cubed over 12.